This principle of magnetic induction was first taught by Michael Faraday. Michael Faraday was described by one of his colleagues as a man almost entirely innocent. Now I would ask you, is that a man that looks almost entirely innocent?
Yes.
No. Let me finish the quote. Michael Faraday was a man almost entirely innocent of the laws of mathematics. How would you like it if your friends said things like that at your funeral? He's totally ignorant. Couldn't do math. And yet, that was true. Michael Faraday wasn't good at math. And yet he gave us some of the most powerful physics that we know today. And that's because he could visualize magnetic field lines. To him, they were real. And because of that, he could see things that others couldn't see. Now, we're going to do some experiments. If I want to get current going around a loop, a copper loop, one way is to hook it to a battery. And that would get current going around that loop. Michael Faraday said, you don't need no stinking battery. All you got to do, hook that up to an ammeter. He says, all you've got to do is take a permanent magnet and move it towards your loop or away from your loop. Now, you seeing the current that's being generated there? Now watch what happens when I put it in there and park it. Very powerful magnet right in the middle of the loop. Do I have any current?
I don't know.
It says 0. Do I have any current?
No.
No, okay. When I pull it out, I get it. When I put it in, I get it. Now, these people could say they don't know because they're seeing my backside. Okay? And when I park it there, 0. What? Don't make me come over there. Okay. Now, let's see if we can understand this. We call it induced current, meaning I can't see the magical battery that's causing this current to flow. Okay, induced current. Now, I hope everyone can see that there's no difference between bringing the magnet towards a loop or holding the loop still and bringing... Let me think that through. There's no difference between bringing the magnet towards a loop or bringing the loop towards the magnet. Did I get it right?
Yeah.
Good. Okay. I need a helper here. Would you help me? Come on down, please. You're just going to hold the magnet. It's not a hard job. Okay. You're just going to hold that. Okay. And here's the loop. Okay. Got your name? Amanda is holding the south pole towards me, and as I push this copper loop towards the south pole, think of this as a hollow plastic loop with charge carriers, positive charge carriers. I am moving not only the loop towards the south pole, but all of these charge carriers in the loop towards the south pole. Now, that's going to give them all the velocity towards Amanda. In a magnetic field that is pointing towards the south pole that she's holding. Now, because those two directions are not the same, I'm going to get a magnetic force. Let's look at a charge up here at the top. It's moving towards Amanda in a field towards that south pole. It's going to be magnetically pushed away from you. Okay? Let's look at a charge down here. It's going to be moving towards Amanda in a field that's towards that south pole. That's going to give a magnetic force towards you. Okay? Now, that's going to cause current to rotate away from you at the top, towards you at the bottom, around this way, induced current. Now, I chose the top and the bottom. I could choose any point. If I choose this point here, towards Amanda, towards the south pole, up. If I chose here, towards Amanda, towards the South Pole, down. So here it's away from you, here it's down, here it's towards you, here it's up. It goes around. Thank you, Amanda. I appreciate it. Okay. Now, does there have to be motion in order for this induced current to exist? Well, Faraday taught us that it didn't. And he gave us this example. If you have two coils, he called this one a primary coil and the one hooked to the ammeter the secondary coil. If you put them next to each other, what you find, let's show these people first, they paid more money. When you connect the battery to the primary, suddenly you get an induced current in the secondary. But then it goes away until I disconnect the primary. And then you get an induced current the opposite direction for a short time. So it's only when I connect and when I disconnect. Okay? When I connect and disconnect. If I leave it connected, that induced current goes to zero. Okay, let's show the cheap seats. So when I connect it, there's an induced current. When I disconnect it, there's an induced current. If I leave it connected, that induced current goes to zero. It's only when I'm disconnecting it or connecting it that I get the current. Okay? So the answer, Faraday taught us, is no. Here's a summary of that little experiment. You close the switch. That gives you current in the primary as long as the switch is closed. We immediately see an induced current in the secondary that quickly goes away, even though I've still got current in the primary. And there's no induced current until I change that current in the primary by disconnecting it. And then I get a brief kind of a spurt of induced current the opposite direction from what it originally was. And then it goes away. So the answer seems to be no. These coils were not moving relative to each other. Okay? Now, what about this? Maybe the B field has to change. Think about that for a minute. With our first experiment, we were taking this permanent magnet and we were changing the magnetic field strength inside that copper loop. It's very weak when it's over here. It's very strong when I put it in the loop. And then I make it weak again. So I'm changing the field strength inside the loop from weak to strong to weak again, and that generates this current. Likewise, if I look at the second experiment, this primary coil becomes a magnet whenever I connect it to the battery. A loop carrying current is a bar magnet. So connecting this is like bringing a magnet nearby, right? And disconnecting it is like bringing the magnet away. I'm changing the strength of the magnetic field through this secondary loop either way. Well, Faraday came up with a thought experiment. He said, suppose you had two copper rails and you hook those copper rails to the leads, the terminals, of a bulb. And then you have a copper bar that's free to ride on those rails. Now, in between the rails, you somehow set up a magnetic field. What can you tell me about that magnetic field just looking at those magnetic field lines?
Uniform?
It's what?
Uniform?
It's uniform. They're always spaced the same distance apart. That means whatever magnetic field strength I have in Tesla here, I got the same magnetic field strength in Tesla there. You also know the field is pointing away from you. Now think of this experiment as something you're looking down on, as if you're just having an out-of-body experience and you're looking down on the experiment there. Now, what Faraday said was, take that copper bar and slide it along the rails. As soon as you slide the copper bar, oh, that's hot. Don't tell anybody. I left it on. As soon as you slide the copper bar, you're also sliding all of those positive charges, the charge carriers, that way in a magnetic field that's that way. Well, that's going to give me a magnetic force on those charge carriers. That's the velocity. That's the B field. The magnetic force would be up. Now, because the charges are free to move up, they do. And that gives me an electric current. But I can't have an electric current there without having an electric current everywhere in that loop. And suddenly the bulb lights. Okay? Now here's the thing. Did I change the strength of the magnetic field inside my copper loop? No, it's the same strength that it was always in Tesla. What I did change was the number of field lines in the loop. And now let's go back and think of the other experiments. And this is where Faraday was a genius. When he saw this bar magnet, he didn't just see the bar magnet. He saw the field lines coming out of the North Pole. And they came out and they spread apart. Okay? Now think of that. Try to be Faraday and think of those field lines coming out and spreading out. I'm holding that field line, pointing it towards that loop over there. How many of the field lines are going through that loop? Not not many, maybe one. But as I get this closer, those field lines that are spreading out, more of them are getting through the loop. And now all of them are getting through the loop. I'm changing the number of field lines going through that loop. Just like I'm changing the number of field lines through that loop. Likewise, with our second experiment, when I connect this to the battery, I turn the primary into a bar magnet. I change the number of field lines through the loop from none when it's not connected to lots when it's connected. In every case, we're changing the number of field lines. Now, we call that the magnetic flux to try to scare you. And we give it a scary Greek symbol, phi, again to try to scare you. The more scared you are of science, the more powerful we as scientists are. That's not true. It turns out the more scared the populace is of science, the weaker and less influence that we have. But anyway, magnetic flux is nothing more or less than the number of field lines. And when we change the number of field lines through a copper loop, it sets up an EMF. Do you remember what an EMF is? A battery, an electromagnetic force, but it's really just a battery, an invisible battery that drives this induced current. Okay? Now, the number of field lines is what we call the magnetic flux. And to calculate it, we multiply the magnetic field strength in Tesla times the area in meters squared. Let me see if I can motivate that formula. We use magnetic field lines to represent where the magnetic field was strong and where it was weak. It was the density of field lines that told us the strength of the magnetic field. So that means that the magnetic field strength was proportional to the number of field lines that fit through a perpendicular area. If I had some area, let's say it was a circle like this, the more field lines I could fit through that area, the closer they would be together and the stronger the magnetic field. Now, if I multiply both sides of this equation by area, the area cancels out over here, and what I get is a measure of the number of field lines. This quantity, B times A, is proportional to the number of field lines. And when I change that through a loop, I generate this invisible battery.